Hi, welcome back to our lecture on a practical guide to quantitative finance interviews. This is our 10th lecture, and today we are going to be talking about, I think, is the most important part, the conditional probability and the Bayes theory. So I want to let you know more in this part, so I'm going to tap in on a little bit about the measure theory, which is the fundamental of the probability theory, and we can make further there so that you can see more clearly about all the conditional things. So, many financial transactions are responses to probability adjustments based on new and most likely incomplete information. So conditional probability surely is one of the most popular test subjects in quantitative interviews. So in this section, we focus on basic conditional probability definitions and theory, okay? So first, the definition, the conditional probability A, conditional on B, is that if probability B is larger than 0, which means it is possible for event B to happen, then the conditional probability is written as probability A intersect with B, A and B happens at the same time, which is the numerator, and on the denominator is the probability that the event B happens alone, okay? And the first important rule about the conditional probability is the multiplication rule, which means if we have multi-events, the first event all the way to the nth event, and if we want them to happen at the same time, it could be rewritten as the probability of event 1 happen multiplied by the probability event 2 happen conditional on event 1 happen, and all the way goes further until to the last one. And it also gives us the law of total probability, which means for any mutually exclusive events. What does it mean by mutually exclusive? Which means if A happens, B cannot happen. If I toss a coin once, if it's a head, then it cannot be a tail, right? So then in that case, by applying the law of application, the application rule, then we can have the formula here, where actually for independent events, probability EF can be written as PE multiplied by PF, and which is also going to be the same for their employment part. And last but not least is the Bayes formula. This formula is quite simple, which just links probability A conditional on B to what? To probability B conditional A. It tells you that as long as you have 3 of all these 4 things, probability A, probability B, as long as you have 1, 2, 3 of these things, you can get the fourth one. Any of these 3, any 3 of the 4 probabilities could give you the last one unknown one, okay? And this is actually quite important, but because if you go to some difficult statistical lessons, you're going to see the whole Bayesian theory is a foundation for things like EM algorithm, which is an important optimization algorithm, and the same for Bayesian boosting, and a lot of Bayesian statistical learning methods. And actually, if you want to divide the whole statistic academia into 2 parts, then one is fragmentist, another one is the Bayesian, okay? That's how important it is. So now I want to talk a little bit more about the conditional probability. So let's start from the simple one, right? The conditional probability A conditional B is just probability AB over probability B, right? But then let's think about that. Let's think A and B has some kind of PDF, right? Then the expectation of A conditional on B equals to something, let's say B. This is what? This is going to be something like A, F, A, B, F, B, D, A, right? This is going to be something like this. Then if you see, we're actually integrating A out, which means what? The conditional expectation is a function of the condition. For example, in our case, this E A B equal to B is going to be, can be rewritten as a function B, right? So it seems a little bit counterintuitive, but let me tell you this. The first way you can think it as a function, because let's say if I toss a coin, then conditional on that a 2 has happened, right? Then the expectation of conditional on I tossed 2 twice, okay? So which means B equal to 2. Then the event A could be something like I have 2 heads or I have 1 tail and 1 head. And all these things are driven by this B, right? So this is one way to expand that. Another thing is that a function is equal to a random variable, which means this expectation of A conditional on B is also a random variable. It's not a number, okay? So I want you to remember that so that when it comes to complex expectations, you can know that you can write this as some FB, not some kind of FA, okay? So now let's come to our today's problem. So the first one is quite simple. Just want to test our fundamental knowledge about conditional probabilities, boys and girls. So part A, a company is holding a dinner for working mothers with at least one son. Mrs. Jackson, a mother with 2 children, is invited. What is the probability that both children are boys? So for this first question, we just need to list out the formula. Event A is what? Is the probability that both children are boys, right? And what is event B? The event B is that conditional on it has 2 children, right? Then probability A, B, and there is one hidden condition here, sorry. We already know he has already at least one son, right? So this is going to be PB, probability A crossing B, which equal to probability boy, boy, right? And on the denominator, it is what? It could be boy, boy, 2 boys, or boy, girl, or girl, boy. Please notice that these 2 should be considered independently because each of them takes up 1/4 probability, right? You cannot just merge them together, okay? So eventually this is going to be 1/4 on the numerator and 3/4 on the denominator, and it gives us 1/3. Now let's come to the part B, right? So Mrs. Parker is already known to have 2 children. And if I'm seeing her working with one of her children and that child is a boy, what's the probability that both children are boys? This time, what is the difference? Well, the thing is that no matter this child is boy or not, right? The gender of the second child is independent of the first one, right? So for the second child, it has 1/2 probability to be a girl, right? And another 1/2 probability to be a boy because it's equal. And what's the probability of both children are boy? Then since the first one is already a boy, then there is only 1/2 probability for both of them to be a boy. Because each children is independent. You cannot say that if my first child is a boy, then the second one must be a girl, right? It's ridiculous. And that links us to the second problem, the all-girl world. So in a primitive society, every couple prefers to have a baby girl. Well, you know, like decades ago or even recently, we still see in some remote areas, people prefer to have baby boys, right? So there is a 50 chance that each child they have is a girl, and the genders of their children are mutually independent. Remember that, mutually independent. If each couple insists on having more children until they get a girl, and once they have a girl, they will stop having more children. And what will eventually happen to the fraction of girls in the society? So again, a lot of interviewees or a lot of candidates will try to answer this question like, eventually we will have more girls. But actually it's wrong. You can just think about our real society. In remote areas, a lot of families want more boys and they are doing the same thing until they get a boy. But still, if we don't consider the extreme cases, like they will kill the girl boy, the kill those girl children or give them less food to eat so that they have to die early. If we do not consider those extreme cases, then actually the ratio for boys and girls is not that extremely, the gap between boys and between the number of boys and girls is not that high, right? It's still around something like 51 or 49. And what's the reason is just saying here, because the gender of their children, the probability of you getting a boy and versus you getting a girl is mutually independent. No matter how many children you already had or you already have, the probability that he is going to be a boy is still 1/2, right? So what will eventually happen to the fraction of girls in society? Expectation of fraction of girls is still going to be the probability multiplied by 1, right? So which is 1/2, the probability of having a girl. So it's still 1/2. The question here is just want to misleading you. He tells you that all girl world, but with a question mark. And for statistician, we need to understand the logic and the reasoning behind this question mark, okay? So now let's come to our third question. It's called unfair coin. So you are given 1,000 coins. Among them, one coin has heads on both sides, and the other 999 coins are fair coins. And you randomly choose a coin and toss it 10 times. Each time the coin turns up heads, and what is the probability that the coin you choose is the unfair one? Then the probability of conditional on this event happen each time the coin turns up heads. Okay, this is our event. That this one is unfair is what? Again, we just use the formula. If it is an unfair one, then the chance is 1/1000, right? And once it is the unfair one, this is the probability of unfair. And conditional on unfair, the event happen is what? It's probability 1, right? As long as it's an unfair coin, we will always get a head. But for the denominator, we have two cases. One, it is what? Probability E over unfair multiplied by unfair, right? Plus 1. Probability event happen over a fair coin multiplied by the probability fair. And for this part, it is what? Since there is only one unfair coin, so we have 999 over 1000 to get a fair coin. And to toss it 10 times, and each time it is head, it is going to be 1/2 to the power of 10, right? And this part is still the same. It is 1/1000 multiplied by 1. And after we take the calculation of this fraction, we can get this is almost around 0.5, okay? So you can see that this ratio is actually higher than you imagine, at least higher than I imagine. And that's the thing that always happens because, for example, for a hospital testing, if you are tested positive for COVID, there is still chance that it is the test cases has problem, but not you are positive, right? And the ratio is not that low, okay? Because you are using conditional probability. So under your condition, it might have a 30 to 40 chances that it is actually the test cases problem, not your own problem, okay? So an interesting story, huh? And now let's continue the next one. It's about fair probability from an unfair coin. So if I have an unfair coin which may bias towards either heads or tails at an unknown probability, can you generate even odds with this coin? So for this question, we need to think back with the techniques I told you last time, right? We need to use the symmetry principle. So first, we can have, if I toss this coin, let's say 2 times, what can we get? We can get head or tail. For the first time, we can get head or tail, right? So there is only 2 cases. And if I call it head is PA, tail is PB, then if I just toss it for once, then it cannot get an even odds, right? If PA doesn't equal to PB. But if I toss the coin for 2 times, then we can get HH, HT, TH, and TT. So TT has a probability of PB squared. HH has a probability of PA squared. But for HT and TH, both of them is what? Is PA multiplied by PB. So we can now design a game, right? As long as I get a head and then tail, I win. So A wins. But if it's a tail following by a head, then B wins. And for both this head or for both are heads or both are tails, then no one wins. And this is going to give us an even odds by symmetry because these 2 are the same. Okay. So now the second last question, the dot game. So I wonder if you haven't seen any American movies where you can see actually the dot game is quite popular in American pub or bars, right? So Jason throws 2 dots at a dot ball, aiming for the center. The center dot lands farther from the center than the first. So if Jason throws a 3rd dot aiming for the center, what's the probability that the 3rd throw is further from the center than the first? Assume Jason's skillfulness is constant, okay? So for this question, the thing we need to do is to do a conversion. Because if we just write it at this problem, let's see, like, I know the 2nd dot lands further from the center than the first. Let's call the first one A, okay, the second one B. Then if this is A, this is the center, let's say this is the center. So I'm going to list like their furtherness in an ascending order, okay? So this is A, and we already know B is further than A. And now we are talking about if we have a C, what's the probability that C is further from the center, which means which is further from the center than the first one, okay? So how many combinations can we have in total? How many combinations and permutations? Let's use the counting method. We can have ABC and what? ACB, right? And what? BAC, BCA, CBA, and CAB. But we already know that A must follow by B. So BA is not possible. So this one has been killed, this one has also been killed, and this one has also been killed. And for the 3 cases left, what can we see, right? For both ABC and ACB, we can have C is further from the center than A, right? So in total, it is 2/3. But now let's think about the general case. The general case is that for the general case, if we want to throw the nth one, then it will always be n-1/n. How is that the case? Because since the first throw is the best among the first n throws, right? Essentially, what I'm saying is that the event that the n+1 throw is the best of all throws is independent of the event that the first throw is the best. And in fact, this, okay, let me rewrite this. Let's say if A is the best of all n rows. And now we are considering the n+1 row, right? This is what we are considering. So this event an+1 is independent of the order of first n rows, which means that we are just trying to place, let's say there are 1, 2, 3, 4, all the way to 1, all the way to n. Okay. And in total, how many intervals are there? If there is n+1, 1, 2, there are in total n+1 intervals, right? And if I'm trying to through one, basically n of this n+1, except from this one, can make me further than the center than the first one, right? Because if I only if I throw here, because this is where the best one here has. If we call 0 is the center, and this is the best one, only if I throw into this interval, I can win, right? Otherwise, I must be further from the center than the A, which is the best one among the first n rows. You see? So the general case is just n over n+1. Okay, like in this case, n equals to 2, and I'm trying to throw the third one, so it's 2 over 3. And now let's come to the next question, the birthday line. So this question is based on the answer of the one question we talked about last time, right? The birthday line. So at the movie theater, a manager announces that she will give a free ticket to the first person in line whose birthday is the same as someone who has already bought a ticket. You are given the opportunity to choose any position in line. And assuming that you don't know anyone else's birthday, and all birthdays are distributed randomly throughout the year, and it is 365 days. So which position in line gives you the largest chance of getting the free ticket? So let's first try to break down this question. To actually being a one and being the first one in line whose birthday is the same as someone who already bought a ticket, when you have like the probability of first n people all having different birthday, right? And multiply by 1. n+1 people, which is me, have the same birthday as one from the first n. So let's first look at this part. This part we already know from the last question that for first n people, they all have different birthday. Then it's going to be on the denominator, it is 365 to the power of n. And it is going to be 365 multiplied by 364 all the way to 365 minus n plus 1, right? And how about this part? Since we already have n people, so the chance is that n over 365. So now we can rewrite it as probability n, we're going to be 365 n plus 1. This is n plus 1, right? If I win as n plus 1. And this is going to be 365, 364, all n multiplied by all these all the way to 365 minus n plus 1. And then we can also know probability n will equal to what? 365n, right? And this is going to be n minus 1. This part is still the same. And the last one is 365 minus n plus 2, right? Okay, and we can also have probability n minus 1, right? And then we can calculate the probability of probability n larger than probability n minus 1, while probability n smaller than probability, also larger than probability n plus 1, right? Because I'm trying to get the largest chance, so I want to get the maximum one. And by solving these two inequalities, what we can get is that for the first one, we can get something by dividing the similar part in these two. So cancel all these things out. And we're going to have n squared minus n minus 365 larger than 0. And for this part, oh, sorry, this one is for this. And for this one, we can have n squared minus 3n minus 363 smaller than 0. So combine these two together, we can get what? We can get n should be 20. And I should be the 20th person in the line. Okay, so now we come to our last question, the dice order. So we threw 3 dice one by one. And what's the probability that we obtain 3 points in strictly increasing order? So for strictly increasing order, there is actually one hidden condition. The hidden condition is that all 3 numbers are different. Right? This is its precondition. This is the precondition, the prerequisite. And the probability of this one is very simple. It is just what? It is just 1 multiplied by 5/6 multiplied by 4/5, right? Which is equal to 2/3. And now among them, because it needs to be strictly increasing. So there is only one permutation to satisfy this one, but in total, how many permutations are there? So it is just a 3rd fraction, and this one is just equals to 5/44. Okay, oh, sorry about this part. This part should also be 6/4. Okay, so this one is going to be 5/18. Okay. No, sorry. Oops. So this is going to be 5/9. So remember, this is 6, not 5. Okay, this is 6 because each time we cannot just cover one face of the dice. Okay, sorry, it's a small problem on me. So it's basically all the questions for today. And next time we are going to continue talking about conditional probabilities by introduce some of the most classic probability theory problems. For example, like the Monty Hall problem and some other things like that. So see you next time. Good luck. Thank you for watching this video.